So in the seventh problem, f is a mapping from a real number to another real number and g is a mapping from a real number to another real number defined by f of x is equals to x power 5 and g of x is equals to x power 4. Then we have to check whether f is a one-to-one function and g is a one-to-one function. If both are one-to-one, then f composite g will be one-to-one. If any one of these is not one-to-one, then f composite g will not be one-to-one. So first let us find whether f is one-to-one. So already we saw in the last class that to prove one-to-one we can do is f of x is equals to f of y. If it implies x is equals to y, then we can consider the function f as one-to-one. We will follow the same steps to do so. F of x is given as, we will take f of x is equals to f of y. F of x is x power 5. Therefore, f of y will be y power 5. So, fifth root, if we take 5 and 5 will get cancelled, x is equals to y. Therefore, f is 1-to-1. The similar step we will follow for g to check whether g is 1-to-1. So same, g of x is equals to g of y, let us take. If it implies x equals to y, then g is one-to-one function. So g of x is equals to g of y. G of x is x power 4. G of y will be y power 4. So if I take the fourth root, it will become x is equals to plus or minus y. So the image is not unique. That is, for one x we have two y's. Therefore, g is not 1-to-1. So if the power of x is an odd number, will not get plus or minus. If the power of x is an even number, will get plus or minus. F is 1-to-1 and g is not 1-to-1. Therefore, f composite g is not 1-to-1. So in the eighth problem, we are given with three functions f of x, g of x and h of x, and we have to show that f composite g composite h will be equal to f composite g composite h. For three subdivisions, we will do one by one. The first subdivision, f of x is given as x minus 1, g of x is given as 3x plus 1 and h of x is equals to x squared. We will first prove take the left hand side. F composite g composite h. As I already told you, we have to complete the portion within the brackets. Therefore, f composite g of x is equals to f of g of x. So, f of g of x in this problem is given as 3x plus 1. Now, we have to use the function f. In place of x, we have to substitute 3x plus 1. So, 3x plus 1 minus 1 plus 1 minus 1 is equals to 3x. Now what we have to do is we have to find f composite g composite h. F composite g composite h. We know the value of h of x as x squared. F composite g of x squared. Now what we have to do is we have to use the function f composite g. In place of x we have to substitute x squared. Therefore 3x squared. RHS. In the RHS we have to find f composite g composite h. First we will complete the portion within the brackets. G composite h of x is equals to g of h of x, where h of x is x squared. We have to now use the function of g. In place of x we have to substitute x squared. So 3x squared plus 1. So next we will find f composite g composite h. F of x value is f of g composite h of x. So f of 3x squared plus 1. The function of f of x, which is x minus 1. In place of x we have to substitute 3x squared plus 1 minus 1. Plus 1 minus 1 will get cancelled, 3x squared. Therefore LHS is equals to RHS. Hence proved. Okay, for this subdivision we have to show this relation. First we will consider the left hand side, f composite g composite h. So first we will find f composite g, which can be written as f of g of x. F of g of x value is 2x. Now we have to use the function f, therefore 2x squared, 4x squared. Next, f composite g, composite h can be written as h of x value is x plus 4, and we will substitute in 4x square. Instead of x we have to substitute x plus 4. So 4 into x plus 4 square. Expanding this in a plus b whole square, a square plus 2ab plus b square. Now the value of a is x and the value of b is 4. So we will get x square plus 2 into a into b, 8x plus 4 square, 16. 4x squared plus 32x plus 16 into 4, 64. Next is RHS, f composite g composite h. So g composite h can be written as g of h of x. G of h of x value is x plus 4. G of x can be written as 2 into x. So 2 into x plus 4, which will give us 2x plus 8. Next is f composite g composite h. So f of 2x plus 8, f function which is x square, 2x plus 8 whole square. So expanding this in the a plus b whole square formula, now the value of a is 2x and the value of b is 8. Therefore this will become 4x squared plus 2 into a into b. 2 2s are 4, 8 4s are 32. 32x plus 8 square, it is 64. Therefore LHS is equals to RHS, hence proved. For the third problem, f of x is x minus 4, g of x is x squared, h of x is 3x minus 5. First we will prove the left hand side, f composite g composite h. So we will consider within the brackets, f composite g of x is equals to f of g of x. F of g of x is x squared. Now we have to use the function of f of x. Instead of x we have to substitute x squared. This will become x squared minus 4. Next, f composite g composite h can be written as f composite g of h of x, whereas h of x value is 3x minus 5. In this function, that is f composite g, instead of x we have to substitute 3x minus 5. So 3x minus 5 whole squared minus 4. A minus b whole square is equals to a squared minus 2ab plus b squared. A equals to 3x, b equals to 5. So if we do so, 3x square is 9x squared minus 2 into 3, 6 into 5, 30. 30x plus 5 square is 25 minus 4. So simplifying this, we will get 9x squared minus 30x plus 21. So this is our left hand side. We will check for the right hand side. Right hand side it is given as f composite g composite h. G composite h is g of h of x. G of h of x value is 3x minus 5. Now using the function of g, which is x square, so 3x minus 5 whole square. So now we have to use the same formula, a minus b whole square. Already we have 3x minus 5 whole square, which we will use it again. It will become 9x squared minus 30x plus 25. Next what we have to do is we have to composite this with f composite g composite h, which can be written as f of g composite h of x. So f of 9x squared minus 30x plus 25. F of x value is x minus 4. Therefore substituting in place of x this 9x squared minus 30x plus 25 minus 4. 9x squared minus 30x plus 21. whereas left hand side is equals to right hand side, hence proved. So in the ninth problem, it is given as f is equals to minus 1 comma 3, 0 comma minus 1, 2 comma minus 9, and this is a linear function. From set of all integers to set of all integers, we have to find f of x. So in this problem, we have to find the value of f of x. I am going to use the value, that is the function f of x, as mx plus c. Why am I using this is because it is given that f is a linear function in this problem, whereas the function of the linear function f of x is given as, whereas the linear function f of x is equals to mx plus c. In this, we will find out the value of m and c. We will substitute the values of m and c. Therefore, we will get the function of f of x. This I am going to consider it as equation 1. For finding the values of m and c, we will take this ordered pair minus 1 comma 3. We all know that this represents x and this represents y. I am going to substitute this in the first equation. So f of x, that is y or f of x, both are same. Therefore, f of x value is 3. M into x value is minus 1. Therefore, minus m plus c. This we will consider it as equation 2. Next, we will consider 0 comma minus 1. Similarly, x comma y, we will substitute 0 comma minus 1 in first equation. F of x value is minus 1, which is equals to m into x value is 0. So m into 0 plus c. M into 0, this will become 0. Therefore, c equals to minus 1. We got it directly. This we will consider it as equation 3. Whereas, we will substitute the value of c in the second equation. Therefore, we will get the value of m. Doing it so, I am going to substitute c equals to minus 1. That is third equation, second equation. 3 equals to minus m. C value is minus 1. I am going to take m to the other side. It will become plus m. 3 to the other side, it will become minus 3 minus 1. M is equals to minus 4. Thus, we got the value of m and c. We will substitute in the fourth equation. If we do so, what will we get? F of x is equals to m value is minus 4. So, minus 4x. C value is minus 1. So, this is the value of f of x. So, in this problem, in electrical circuit theory, a circuit C of t is called a linear circuit if it satisfies the superposition principle given by C of A T1 plus B T2, which is equals to A into C of T1 plus B into C of T2, where A, B are constants in this. Show that the circuit C of t is equals to 3t is linear. What we have to do is, we have to show the C of t is equals to 3t is linear. When we can say this as linear is when it satisfies the superposition principle. We can say that C of t is equals to 3t is linear. Okay. So what will we do is, we will take this C of t is 3t, which is given. If it is C of AT1, what we can do in the same method, if we want to write, we can write it as 3 into AT1. Similarly, if it is C of BT2, we can write it as 3BT2 by the same format. Now, we will take the left hand side and we will prove the right hand side. If this superposition principle for this values, if it satisfies, we can say this is linear. I am going to consider the left hand side. We have to bring the right hand side. C of AT1 plus BT2 equals to, so if it is C of t, it is 3t. Similarly, if it is C of this value, we can write it as 3 of AT1 plus BT2. Now we can split it into two terms, 3AT1 plus 3BT2. We can interchange the positions. So this is 3AT1 is A into 3T1 plus B into 3T2. A into 3T1 can be written as C of T1. Similarly, 3 of T2 can be written as C of T2. Whereas this is the right hand side. Therefore, we took the left hand side and brought the right hand side for this function. Therefore, C of t, which is equals to 3t, is linear. In today's class, we saw composition of functions and we have solved the problems of exercise 1.5. If you have any doubts, you can post your questions in the comment box. In next class, we will see exercise 1.6, which is of multiple choice questions, and we will solve the problems under unit exercise 1. Thank you.